Hello and welcome back to G Fun Facts Online, your go-to source for the most amazing breakthroughs in science and technology. Today, we're diving deep into the world of materials science, exploring a fascinating class of materials that are literally built on forces so weak, scientists once thought they were useless for creating anything strong. I'm talking about van der Waals frameworks. Now, for the longest time, if you wanted to build a robust, porous material, think of a microscopic sponge. You'd use strong chemical glue, like covalent or coordination bonds. These are the heavy lifters in materials like covalent organic frameworks, or COFs, and metal organic frameworks, or MOFs. Van der Waals interactions, on the other hand, things like London dispersion forces or dipole-dipole interactions, were seen as too flimsy, too non-directional. Imagine trying to build a skyscraper with sticky notes. That was the general consensus. But, as science often shows us, assumptions are made to be challenged. Fast forward to early 2024, and a groundbreaking paper hits the press. Researchers at Kyoto University announced they had done the seemingly impossible. They developed the first three-dimensional van der Waals open frameworks, which they call WaaFs. That's WaaFs. So, how did they turn those sticky notes into something capable of building a stable, porous 3D structure? The secret lies in clever design and some rather large building blocks. They used precisely engineered molecular units, specifically octahedral metal organic polyhedra or MOPs, that are larger than 2 nanometers. Think of these MOPs as Lego bricks with large, flat, aromatic faces. These large faces dramatically increase the contact area between the bricks, and when you have a lot of these weak van der Waals forces acting together over a large area, their cumulative strength can be surprisingly mighty, sometimes even comparable to the stronger bonds found in MOFs and COFs. And these WaaFs aren't just a scientific curiosity. They have some truly impressive characteristics. For starters, they exhibit high thermal stability, meaning they can keep their structure intact at temperatures up to 320 degrees Celsius or 593 Kelvin. That's pretty hot. Even more astounding is their specific surface area. We're talking numbers that can exceed 2,000 square meters per gram. To put that in perspective, a single gram of this material could have an internal surface area larger than several tennis courts. This incredible porosity is a golden ticket for applications like gas storage and separation. Another really cool feature of these WaaFs is their potential for reversible assembly and disassembly in solution. This isn't just neat from a lab perspective. It's a huge deal for making them easier to synthesize, process, and potentially even recycle on a large scale, which is always a big win for industrial applications. So, what does this mean for the bigger picture? Well, this research basically throws open a new playbook for designing porous materials. It tells us we can harness these subtle, weak interactions to create robust and highly functional architectures. The ability to tune the porosity and chemical stability of WaaFs makes them super promising for a whole bunch of cool stuff. For example, their massive surface area and tunable pore sizes are perfect for selectively grabbing and storing gases like hydrogen for clean energy, methane, or even carbon dioxide to help combat climate change. They could also act as tiny reaction chambers for catalysis, potentially making chemical reactions more efficient and selective. Imagine materials that can pull water vapor straight out of the air in arid regions, or super-sensitive chemical sensors that detect tiny amounts of specific molecules. The possibilities are really exciting, and the story doesn't stop with 3D WaaFs. Research into 2D van der Waals frameworks and heterostructures. Think of materials made of single atomic layers, stacked like sheets of paper, held together by these same weak forces, is also booming. These layered materials have their own unique set of electronic, optical, and mechanical tricks up their sleeves, with potential uses in next-generation electronics, optoelectronics, and catalysis. Controlling how these 2D sheets stack and interact is key to unlocking their full potential. There's also a broader family of materials called porous organic molecular materials, which includes things like hydrogen-bonded organic frameworks, HOFs, and porous organic cages, POCs. These also rely on weak non-covalent interactions, including hydrogen bonds, which are a type of van der Waals force. A big advantage here is that they can often be processed from solutions, which is great for making things like membranes for separating gases, filtering ions, treating water, or even desalinating seawater. HOFs, in particular, use hydrogen bonds, often alongside other weak forces, to build their spongy structures. The challenge here is making them stable, because hydrogen bonds are weaker than covalent bonds, but scientists are getting clever with strategies like designing rigid building blocks or encouraging multiple hydrogen bonds to form. Of course, it's not all smooth sailing. There are still challenges to overcome. For those 2D materials, controlling how the layers clump together while keeping their desired properties is an ongoing puzzle. For the 3D WaaFs and other materials built on weak interactions, ensuring they stay structurally sound over long periods and under real-world conditions like pressure, temperature changes, and chemical exposure is absolutely crucial. Predicting exactly how these frameworks will assemble, especially when you have multiple different building blocks, also needs more work, both in terms of our theoretical understanding and our lab techniques. So, what's next for the world of van der Waals frameworks? Future research will likely zoom in on designing brand new molecular building blocks. Think custom-designed Lego bricks with specific shapes, sizes, and surface features to create frameworks with precisely tailored pores and properties. Scientists will also be working hard to understand exactly how the delicate dance of these weak interactions dictates the final structure and performance of the materials. This means we'll also need advanced characterization techniques to actually see and measure these weak forces at work. And of course, the hunt is on for new applications, perhaps in biomedicine, like for delivering drugs, or in even more advanced separation processes and novel electronic devices. Improving the stability and making these materials easier and cheaper to produce, especially for things like HOFs, is also high on the to-do list. In conclusion, engineering materials using van der Waals interactions is a frontier that's expanding at lightning speed. Recent breakthroughs have shown us, without a doubt, that these once overlooked weak forces can be cleverly orchestrated to build remarkably stable and incredibly porous frameworks. These materials hold immense promise for tackling some of the biggest challenges we face today in energy, the environment, and technology. As our ability to understand and control these delicate forces continues to grow, get ready to see van der Waals frameworks pop up in some truly innovative solutions. That's all the time we have for today on Fun Facts Online. Thanks for tuning in, and be sure to join us next time for more fascinating facts from the world of science.